The universe expands, yet the truth remains, still within.
The universe may be far more complex than we can imagine. For most of human history, the universe appeared simple. The stars moved slowly across the sky. The sun rose every morning, and the world around us seemed stable and predictable. Ancient observers believed that the cosmos was ordered and understandable, a system governed by clear patterns that could eventually be fully explained. Even when science began to develop during the last few centuries, many scientists believed that the universe might ultimately behave like a perfectly functioning machine. If we could discover all the laws of physics and measure all the properties of matter, then perhaps everything about reality could be predicted with certainty. But as science progressed and physicists began examining the universe at deeper levels, something unexpected happened. Instead of becoming simpler, reality became increasingly mysterious. Every new discovery revealed layers of complexity that challenged our understanding of how the universe actually works. One of the first major transformations in our understanding of the cosmos came with the realization that the Earth is not the center of the universe. For thousands of years, people believed that the sun, moon, and stars revolved around our planet. This idea seemed obvious because the sky appeared to move while the Earth felt motionless beneath our feet. But observations made by astronomers such as Copernicus, Galileo, and Kepler revealed that the Earth is only one planet orbiting the Sun. Our solar system itself is only a tiny part of a much larger structure known as the Milky Way galaxy. Today, we know that the Milky Way contains hundreds of billions of stars. And beyond our galaxy, there are billions of other galaxies scattered across the observable universe. Each of these galaxies contains enormous numbers of stars, planets, and cosmic structures. The scale of the universe is so vast that light itself, traveling at nearly 300,000 kilometers per second, can take billions of years to cross the distances between galaxies. Yet even this enormous cosmic landscape may represent only a small part of reality. When astronomers study the motion of galaxies, they discover something deeply puzzling. The visible matter in the universe cannot explain the gravitational forces observed at large scales. Galaxies rotate far too quickly to be held together by the stars and gas we can see. According to the laws of physics, these galaxies should have torn themselves apart long ago. But they have not. Something invisible is holding them together. Scientists call this mysterious substance dark matter. It does not emit light, reflect light, or interact with electromagnetic radiation in ways that telescopes can detect. Yet, its gravitational influence is clearly visible. Dark matter appears to surround galaxies in vast halos that extend far beyond the visible regions of stars. Current estimates suggest that dark matter makes up about 27% of the universe. But the mystery does not end there. Even more surprising is the discovery that the expansion of the universe is accelerating. For much of the 20th century, scientists assumed that gravity would gradually slow the expansion that began with the Big Bang. After all, gravity pulls matter together, and over billions of years that attraction should reduce the rate at which galaxies move apart. But observations of distant supernova explosions revealed the opposite. The expansion of the universe is speeding up. Galaxies are moving away from each other faster and faster over time. This acceleration appears to be driven by something known as dark energy. Unlike dark matter, which pulls matter together through gravity, dark energy seems to push space itself outward. It acts like a kind of pressure embedded within the fabric of space. Dark energy may account for nearly 70% of the total energy content of the universe. This means that everything we can see, stars, planets, gas clouds, and galaxies, represents only about 5% of the cosmos. In other words, 95% of the universe is composed of things we still do not fully understand. Yet the mysteries of the universe extend far beyond dark matter and dark energy. Another extraordinary discovery of modern physics is that time itself is not absolute. Before the 20th century, scientists believed that time flowed at the same rate everywhere in the universe. Seconds, minutes, and hours were thought to pass uniformly regardless of where you were or how you moved. Einstein's theory of relativity changed this understanding completely. According to relativity, time and space are connected in a four-dimensional structure known as space-time. Massive objects, such as stars and black holes, distort this structure, bending the geometry of space around them. Objects moving through this curved space-time follow paths that we perceive as gravitational motion. But relativity also reveals something even more remarkable. Time itself can slow down. Clocks moving at extremely high speeds tick more slowly than clocks at rest. Clocks located in strong gravitational fields also run more slowly than clocks far away from massive objects. These effects may sound like science fiction, but they have been experimentally confirmed with extraordinary precision. In fact, the satellites used for global positioning systems must account for these relativistic effects in order to provide accurate navigation on Earth. While relativity reshaped our understanding of gravity and space-time, quantum mechanics transformed our understanding of matter itself. When physicists began studying atoms and subatomic particles, they discovered that the microscopic world behaves in ways that defy classical intuition. Particles, such as electrons, do not behave like tiny solid objects. Instead, They exhibit both particle-like and wave-like properties. An electron can spread out across space like a wave, existing in multiple possible positions simultaneously until it is measured. This phenomenon is known as quantum superposition. Even more astonishing is the phenomenon of quantum entanglement. When two particles become entangled, their properties become linked in such a way that measuring one particle instantly affects the other, even if they are separated by enormous distances. Experiments have confirmed this behavior many times. It suggests that reality may be more interconnected than we previously believed. These discoveries raise profound questions about the nature of reality itself. What does it mean for a particle to exist in multiple states at once? How can two particles remain connected across vast distances? And what role does observation play in determining the outcome of quantum events? Physicists are still debating these questions today. Another mystery arises from the study of black holes. These objects form when massive stars collapse under their own gravity at the end of their lives. The resulting gravitational field becomes so strong that nothing can escape from the region surrounding the collapsed core. Not even light. The boundary surrounding a black hole is known as the event horizon. Once something crosses this boundary, it cannot return to the outside universe. For many years, scientists believed that black holes simply swallowed everything that fell into them. But quantum physics suggests something more subtle. In the 1970s, physicist Stephen Hawking discovered that black holes may slowly emit radiation due to quantum effects near the event horizon. Over extremely long periods of time, this radiation could cause black holes to gradually evaporate. This discovery created one of the deepest puzzles in physics. If a black hole eventually disappears, what happens to the information about everything that fell into it? According to quantum mechanics, information cannot be destroyed. Yet black hole evaporation appears to erase it. Solving this paradox may require a deeper theory that unifies quantum mechanics and gravity. Some scientists believe that such a theory may reveal that space itself is not fundamental. Instead, space may emerge from deeper relationships between quantum systems. In certain theoretical models, the geometry of space-time arises from patterns of quantum entanglement. If this idea is correct, the universe may not be built from objects moving through space. Instead, space itself could emerge from networks of connections between fundamental physical systems. Reality, in this view, may be fundamentally relational. The universe may be less like a machine made of parts and more like a complex web of interactions. As scientists continue exploring the cosmos, powerful new instruments are revealing structures that were once impossible to observe. Advanced telescopes are mapping the distribution of galaxies across billions of light years, showing that matter in the universe forms enormous filaments and clusters resembling a vast cosmic web. Particle accelerators are probing the behavior of matter at extremely high energies, searching for new particles that could explain dark matter. Gravitational wave detectors are observing ripples in space-time, created by collisions between black holes and neutron stars, billions of light years away. Each new discovery provides another piece of the puzzle. Yet the deeper we investigate the universe, the more mysterious it becomes. Instead of revealing a simple and predictable cosmos, modern science has uncovered a universe filled with hidden structures, unknown forces, and unanswered questions. Perhaps one day, humanity will develop a deeper theory that explains how all these pieces fit together. Or perhaps the universe will always remain partially mysterious. But the search for understanding continues. Because every time we look deeper into the cosmos, we are not just exploring the universe. We are exploring the nature of reality itself, and the deeper we look, the more extraordinary it becomes. Still within,